Okay. Good morning, everyone. Yeah, I think it's time to let's start. It's a really great pleasure for me to welcome ChengXiang, and he already call himself Cheng to make it easier. So Cheng is a good friend and a colleague of mine. So we know each other more than how many years, 15 years or so. So, and you know. Oh, let me start this. Cheng is currently a professor at the computer science at the University of Illinois at Urbana-Champaign, and he's also the visiting faculty scholar, and I think it's a sort of endowed chair kind, and at this university. And then he has two PhDs. One is a PhD in computer science from the Nanjing University, one of the best university in China. And then he further completed a PhD in the language technology at the CMU. And since then, he began working in the field of the information retrieval, text mining, and then now began even brought out to much broader areas like medical domain, knowledge and engineering in the medical domain. And Cheng has a really successful career just in terms of the scholarship. He has published more than 200 papers, and many of them are highly cited, and including the best paper award in the CCRI, right? Is the flagship conference at the information retrieval field. And he's also well recognized in the field, and he has chaired the conference at CCRI. And he's also had many editorial positions, in the field. And it's editor-in-chief of the Springer information retrieval book series, including those. And he also has numerous awards. I think maybe one of them is the most impressive is as a presidential career award is issued by White House, right? So people always say the 6-degree connectivity among humans, then you just after you shake his hand, you're 1 degree away from a president. Of course, it's not current president. Now I have to wash my hands. Okay, so Cheng works on right now. He's also a major player in another big BD2K center. It's called NOIM at the University of Illinois, UIUC. And I invited him just to come over here to explore just how we can collaborate to potentially say we mine a lot of the biological data, and their central expertise manage the existing knowledge and how to utilize them, and then how we can really make the data and the knowledge meet together. That's the whole idea of this BD2K, so from data to knowledge. Without further ado, welcome, and we look forward.
Thanks, Xinhua, for the kind introduction, and thanks for the opportunity to give this talk. It's really my pleasure and my honor to be able to give this talk here. And it's also a very special experience for me because I academically grew up here. As Xinhua said, I did my PhD, second PhD at Carnegie Mellon University, not far away from here. And I also used to go to talks at Pitt. I learned from Greg's pioneering work on Bayesian-based network that benefited a lot in our research. More importantly, I learned from Xinhua. Actually, he's the one that got me really interested in this field. And since then, I have become very interested in this field. I just did not get enough time to work on this. We also published some joint papers, and I'm very excited to have the opportunity again to talk to him and many of you to discuss opportunities to collaborate, and just had a great discussion with Richard for some potential opportunities, and certainly looking forward to also help the Knowing Center at UIUC and the Causal Discovery Center here to collaborate. I think there's a great opportunity to put the intelligent algorithm and analysis methods here, maybe in that kind of general practical system. And I talk a little bit more in the end about the Knowing Center. So today's talk is mostly about the traditional Chinese medicine patient record analysis, but I think some of the methods can be generalized to to process Western medical records, and some of the ideas may be even more general. So I hope to broadly explore all kinds of collaboration opportunities. I should say that I've prepared more slides than I can possibly cover, and that's by design because the slides will be available for you to review later. So I want this to be relatively complete, but then during the talk, I will intentionally skip or make a brief on some of the slides that are less important to focus on the high-level messages. So you might see me going quickly over some of the slides. Right, so basically, it's a brief outline. I also start with some introduction of my group and some broad picture of what we are working on, because some of the general ideas might be applicable to your problems and as well. Most of the time will be spent on the traditional Chinese medicine data analysis, and finally I talk about the center and some potential opportunity for collaboration. So my group mostly has been working on text information management and analysis, and a lot of PhD students working with me, generally speaking, and I want to use this slide to also thank a lot of funding agencies and collaborators that have helped me get all those research done. So at a very high level, our goal is to help people make use of big data, and particularly text data, which is what I have been working on a lot. And the general picture is, in order to make use of any data, you first have to go through a process of retrieval, where you reduce the large amount of raw data into a smaller but much more relevant data. Because for any particular problem, what matters is the relevant data. We need to get to that subset of data. This is not just for improving efficiency, to avoid touching a lot of non-relevant data, but also to increase the quality of the data. So that's the retrieval stage. And then the next stage is to further digest the content and to turn the data into insights, into knowledge, into actionable knowledge that can actually help decision making. Right? I call it text mining. So roughly speaking, this is the process that we work on. The specific work developed by me and my students and my collaborators is more focused on general methods that can be applied to any natural language. And these methods tend to be statistical. That's why Bayesian built network, and those techniques are very useful. And the downside is that they tend to be relatively shallow. So they are not as deep as natural language processing work that often relies on learning from training data created by people. So the two kinds of methods should be complementary with each other. We also emphasize optimization of the collaboration and between humans and the computers. And this is because in many of the tasks that we're interested in, especially in research and scientific discovery, here humans play an important role. So computers are tools to help us, but then computers can be very intelligent, can be very powerful as well, as already demonstrated in some of your work here. In causal discovery, humans cannot possibly see all those patterns or accurately see that. So but we need to kind of make the two collaborate with each other more effectively. And we emphasize a lot on that, how to make use of human expertise to help computers in return to make the computers more intelligent, and there should be a dialogue, an iterative loop. So these are the general techniques. I think when we think about the applications to this domain, there are many connections, and we think about the connections in two angles. One is the data and information handle. Here I list some data that are textual or semi-structured, right? So biomedical literature, medical records and health forums, etc. And we tend to have to deal with a lot of such data where some of our techniques can be applied. The other angle is the users, and here we are hoping to help researchers and physicians, patients, etc. So when we connect the two, there will be a gap. There will be also a lot of needs for powerful systems to assist these human users in decision making or in optimizing the task. And this is really a high-level connection, I think, of some of our work and what you may be working on. More specifically, in the medical and health informatics domain, we worked on two kinds of problems. One is medical case search. And this is very important for precision medicine in practice. And once you have a patient, how do you match this patient accurately with other patients that are very similar to you? Or do you match the cases with cases reported in literature? or even social media, and we need to bring these cases together. This is one angle. The other angle is medical knowledge discovery. That's when we would ideally combine medical records with biology knowledge base or literature, and a lot of sources of knowledge or data together to perform integrative analysis to hopefully discover new medical knowledge like about side effects or effectiveness of treatment, etc. This is at high level, but today's talk is more focused on the traditional Chinese medicine data analysis, and mainly 3 lines of work. One is disease profiling, and I say more about that obviously, but he just briefly mentioned the flavor of the work. The second line is patient subcategorization, clustering of patients, and the third is to do survival analysis of different groups of patients. In each of these lines, we also used some computational ideas that, number one, may be generalizable to process Western medical records, and they should be general. And number two, some might provide insights also about how we might do integrative analysis of medical records and biological databases. So in the first line, we'll talk about some ideas on using probabilistically generated models to analyze medical records. The second line, we'll try to explore how to use the medical dictionary, the additional knowledge from the domain, to help improve clustering. In the third part, we'll talk more about how to integrate a lot of knowledge from different sources in a computational way to help fill in missing values in medical records to make semantic matching more accurate. So to start with some background about the traditional Chinese medicine, and then, so why are we interested in that? And yesterday we had a conversation with Harry, and then he also asked a question about, this is something that seems more empirical, and then, so yeah, this is actually indeed the some of the problems that exist in the domain, but this is basically medical practice that has been popular, especially in China, for many years. They have accumulated a lot of empirical knowledge that doesn't often have a good scientific foundation. And that actually creates problems for inheriting the knowledge and passing the knowledge to new generations. And also, this field itself needs help in how, systematically summarizing the knowledge, make it more scientific and more systematic. But on the other hand, these are experimental results of a lot of herbs, natural products, if you want, on a lot of patients. And so they contain a lot of empirical knowledge about what might work for what kind of people. And so there's an opportunity to actually mine this kind of data to help medical knowledge discovery. Now, I don't know how many of you can recognize this face. Some are smiling, some must have already recognized the face. But she was a Nobel Prize winner in 2015 together with 2 other scientists because of the discovery of artemisinin. I don't know if I pronounced it correctly, but then this discovery was enabled by traditional Chinese medicine. They initially tried some herbs that seemed to be effective for malaria, and this was documented in some old books. It inherited the traditional Chinese medicine knowledge, but from there they could then pin down to exact chemical ingredients that were playing the role, and that led to more scientific discovery. So that's something that we hope to be able to achieve by computational approaches, and this will help humans to discover more things like that. As the general vision is to think about all these medical records in traditional Chinese medicine that contain symptom descriptions, their assessment by physicians, and also more importantly, precise descriptions of the prescribed herbs with the exact amounts, etc. We treat these as experimental data on a large number of patients, and we do have a lot of such data. And from here, we hopefully can find what kind of herbs, when combined, would be effective or tend to be more effective for what group of patients. And the group of patients can be defined based on phenotypes, but also more discriminatively, perhaps grouped based on symptoms that are often observed by traditional Chinese medicine doctors, but not always noticed in Western medical records. For example, the physicians would look at your overall health stats, look at your towns and your pulse and consider your history. There's a lot of different characteristics of individuals. So this precision medicine or this individualized treatment is actually the central philosophy of traditional Chinese medicine. And so that you can hopefully find the groups of patients that share certain phenotype and or characteristics in general that tend to benefit from certain combinations of herbs. From there, we can pin down to effective chemical ingredients in those herbs, or we can go even directly to the chemical ingredients for analysis. Right? And then from there, we can then have a bridge to biological databases, biomedical knowledge bases, and pathway knowledge information, and also Western medical records. Once we can combine all these, we can perform more rigorous scientific research to test the hypothesis. Hopefully that would lead to new discovery of medical knowledge and also to help provide a scientific foundation for the traditional Chinese medicine. So that's really the high-level vision. And as I said, individualized diagnosis and treatment is at the center of the philosophy of traditional Chinese medicine. And the positive impact of this in terms of experiment is that now we naturally generate a diverse set of hypotheses to be explored, and then the physicians would be tuned toward the most promising hypothesis, and they will try to explore efficiently the hypothesis that seems to be most promising. So from this data experiment perspective, we also naturally will grow the space of hypothesis being tested, and we'll accumulate more and more data to help us make a discovery using computational methods. So a lot of the work that we've done here is done in collaboration with the data center of traditional Chinese medicine in Beijing. They have been collecting data for about 10 years. And there are now over 300,000 clinical cases in their data warehouse. And I have a few key collaborators that I also want to thank here. There are two doctors, Dr. Zhang and Dr. Liu in Guang'an Hospital, Chinese Academy of Chinese Medical Sciences. And there is also a professor in China who's affiliated with this Chinese Academy of Traditional Chinese Medicine. Also, that's Professor Zhou from Beijing Jiaotong University. But the work is mostly done by two of my PhD students, ChengXiang and Edward Huang. And they are also very interested in generating this topic. So there are opportunities to collaborate. I think we'll see interactions with them. Okay, so now I'm going to talk about these 3 lines of work. And that's where I will likely go quickly over some of the slides, and just in the interest of time, and you can take a look at some of the details later both in those papers and also in these slides. The first line is disease profiling. And the problem here is we want to kind of summarize what are the patterns that we see in these medical records in terms of what kind of symptoms typically are associated with a particular disease. And here symptoms are broadly including a lot of symptoms that are kind of only meaningful from traditional Chinese medicine perspective, and information about your pulse, etc. Right? And also to characterize what kind of herbs have been typically prescribed for this particular disease. And this would allow us to then infer the correlations between symptoms and the herbs, and then we're not getting to the causal level yet. And then this obviously is still shadow analysis of this, but there's potential to do more causal analysis here, and if we can see any interesting effectiveness patterns. So here's an example of the analysis that we would like to get for patient record. We hope to infer the distribution over the possible diseases for a patient. A patient might have multiple diseases, and we want to infer that. And then for each disease, we want to have a distribution over symptoms. And And then we also want to have a distribution over the herbs, typical herbs prescribed for treating this kind of disease. So that's the input that we hope to generate by using a generative model from our data set. One challenge here is that we have mixed vocabulary here. And because the symptoms will be mixed, and then you have multiple diseases, and we need to figure out the kind of the associations of these symptoms and diseases. So that's where we would use a probabilistic model to do that. And so the solution proposed is a conditional probabilistic topic model, and I call it topic model here because the model is kind of adapted from some model people have proposed for modeling text data, where topic is used. So here we assume each disease is a topic, and this particular disease would have its own distribution over symptoms and its own distribution over herbs. That's the assumption here. Of course, one difference from the previous work on topic modeling is that we have a strong prior on the topics here. That's the disease. In fact, we can lock the topics to a direct one-on-one mapping to the diseases. The difference from some previous work on analyzing this data is that here we're trying to actually model the causal relation here. The assumption is that the symptoms are caused by the disease condition, and the herbs prescribed are also caused by the inferred the disease condition from physician's perspective. So the generative model would then use the disease to kind of generate the symptoms and the herbs. So more formally, the model looks like the following. So we have a model for the CRS is a symptom, H is a herb, and then for a particular patient, we are considering all the diseases of this patient, and then there's D is a disease. So this part is what we observed. We observed the symptoms, herbs, and the disease diagnosis that the doctor has recorded in the patient record. But inside the model, we have a likelihood of patient T having a particular disease here, and then these two are the two distributions of the data that we will observe if the patient really has this disease. And this is just a basic model that's also similar to what people have used for modeling text data, only that we have kind of two kinds of vocabulary. We separate them to hopefully learn some correlations here. And then we just fit this model to our data set, and the optimization is a maximum likelihood estimate, and we use the EM algorithm to solve the problem, to recover these quantities that we are interested in. And the data set we used is a little bit over 10,000 patient records in digestive system treatment, and with about 3,000 symptoms, 97 diseases, and 650 herbs. And here's some specific information about the disease, and mostly stomach problems. And the ground truth that we use for some of the quantitative evaluation is a dictionary in traditional Chinese medicine. They would document what kind of herbs tend to be effective for certain symptoms. And this is again human created knowledge. It's not really based on scientific evidence, or all kind of informal evidence. But these are good enough, we thought, to help us validate the model's ability to kind of mimic a physician in traditional Chinese medicine doctor. So as I just said, the output of the model would be these probability distributions, and we can use them to do various things. But first, just some sample examples of the distributions of the three diseases, and that are ranked high based on entropy measure. And then these are, this is the disease name, and these are some distribution of the symptoms. And sorry that you won't be able to read the Chinese version, but then there are some English translations here. And for the symptoms, you can see they're not the typical, Western medicine symptoms, and so they are more based on some of the subjective assessment of people, but these are sometimes useful for fine discrimination of patients and to create interesting subgroups that might show different behavior in survival analysis or in treatment responses. And these are the typical herbs prescribed for these diseases. And then these symptoms and herbs are mostly verified by the physician that we work with, and they all make sense to them. The top ranked ones, as you go down, there will be some questionable ones, but the high probability ones seem to make a lot of sense. When I just talked to Richard this morning, and he was interested in the understanding of the side effects of these natural products, and also mentioned some relevant research here where people are experimenting with detailed analysis of these natural products. So this kind of analysis can perhaps suggest some interesting hypotheses to look into for potential discovery of more low-level knowledge about the disease mechanism and the treatment. Here are some comparison results of the recommended herbs based on our probabilistic model with what are actually prescribed by the physicians. And we look at some future patient records and then pretend that we don't know what have been prescribed, and then use the system, use the model to predict what herbs would be prescribed, and then compare that with what actually happened in those cases. And there are a lot of shared herbs that we recommend, but there are also some differences. Again, this might provide some insight for traditional Chinese medicine doctors to look into the variations of these prescriptions. This is a quantitative evaluation of the symptom herb annotations, the associations. So we use these two distributions to compute the correlation of a symptom and herb. Basically, do they tend to have high probabilities from the same disease distribution? And then we compare that with that dictionary and to do the quantitative evaluation. Here we show that the method, this is probabilistic method, is better than another baseline method that's based on frequent pattern mining. And because those methods tend to have hard threshold to decide the frequency of patterns, and you see, it doesn't really work well as we do this kind of trade-off here. And again, here are some sample results of the association, and again, there are some new associations that were found by using this probabilistic model. And we did not find them by using the frequent pattern mining approach. And so again, these are useful for kind of summarizing the traditional Chinese medicine knowledge. So basically, here we presented a new probabilistic model for modeling macro records. I think it can be potentially adapted to model the Western medical records, and so certainly it's possible to serve as a basis to build a practical system to help traditional Chinese medicine practicing in China or in some other countries. And from experimental perspective, I think this can help them to focus more on the most promising prescriptions to experiment their variations. In the future, I think we really need to get into the analysis of effectiveness of those treatments. We have not been able to do that. We just started doing that. I don't have the results, but one idea some students are trying is to look at some of the keywords. Sometimes they would say this symptom gets better. What we need is to build a table of these symptoms over a timeline, and then have an assessment of how well the patient has been recovering in this dimension along those symptoms. And if we can have that, then we can make a contrast and then try to do more analysis of the effectiveness. This is really a very important step. And so some results are interesting when the student just look at the keyword. This is getting better. This unfortunately means we have only a small sample, because not in all cases we have this. But in the future, perhaps we can have a system that would enable doctors to say more, to score a symptom. And that takes a little bit more effort, but then the benefit is that now we have annotated the response. and that would be really, really helpful. This is the case of human-computer interaction here, collaboration, where the human would make a little bit more effort, but not that much, hopefully, but it will help a lot in the system part to learn to do analysis.
Do you have any sense, and have you thought about modeling the individual physician effect on the choice of the therapy so that you can see maybe through modeling that, you can see which therapies are consistent for given conditions across clinicians?
Yeah, that's an excellent question. No, we have not been able to do that because the data set here actually is collected by this doctor who strongly believes in this methodology. So he kind of kept his own data. That's an excellent question. I think if we can do this for all data from other doctors, we can look for the common patterns. Those presumably have higher confidence, and we can also examine their variations. So that's an excellent suggestion. I think we have that in mind as well. We should indeed want to do that, and I think it's feasible through collaboration with them to do that. Yeah, feel free to interrupt me also if you have other questions. And okay, so the next work is about the subcategorization. So here we hope to explore the use of the dictionary to help improve the similarity measure and the clustering result. Now, why do we want to do subcategorization? Well, in general, in precision medicine, you would be interested in subgroups of people that might behave similarly but different from other subgroups, even if they have the same disease. Cancer typically has many subtypes, but even for the same subtype, sometimes depending on their health conditions, other environment, there will be differences. So this is the idea, and here it's interesting because in traditional Chinese medicine, they look at some symptoms that are not necessary or definitely not captured in Western medical record. But those are often also reflection of phenotypes or some kind of variations of individuals in the particular disease domain. Now, don't worry about the actual interpretation of these, and again, we have Chinese and English translations here, but mostly you can see these, the value from precision medicine perspective is these can give us subgroups of patients that may originally just share the same group based on biomarkers, let's say, from genome. But here we might be able to distinguish different patients based on their history of these symptoms. The approach we explored is just an ordinary clustering approach, but we use herbs and symptom information together. One challenge here is that the medical case descriptions are sparse, and when you match them, there are vocabulary variations that don't really match each other. So the main solution here is to leverage the traditional Chinese medicine dictionary to kind of help fill in some of the gaps. So we can, from the dictionary, we can infer these herbs tend to be prescribed for similar diseases, and so they are supposed to be effective for the same diseases. Therefore, we can assume that these two symptoms can kind of match each other, although weakly, not as good as exact match. But these two symptoms clearly are different from two completely different symptoms. Symptoms or herbs. Either way, both can be the similarity of two symptoms or similarity of two herbs can be inferred from the dictionary, from association perspective, and these can help us match the medical records hopefully more accurately. That's the hypothesis, and then the results did show that it helps improve the accuracy. So from system perspective, this is just to take the dictionary, which has entries like this. This herb is typically prescribed for this kind of symptoms. And then we use an embedding approach to learn a vector representation of these herbs and symptoms so that if they are strongly associated together, their dot product would be high. And this DCA embedding would be used to expand the patient record with additional related terms that would help us better match cases where there aren't many exact matches. So this allows us to create these groups, and then we hope to then further analyze the response of these groups, and I talk a little bit more about the survival analysis, where we are, for the cancer patients, we know that there are some information about their survival time, and then that can be correlated with these groups. To evaluate this, we again used some curated data set by our physicians, and there are actually multiple levels of categories. And so this is a database with a little bit over 2,000 medical records with 3 level 1 labels and 51 level 2 labels, and then 274 level 3 labels. And here are some examples of this. And so this those are our kind of ground truths, and that we want to use to validate our algorithm. The algorithm would be just doing clustering, we do hierarchical clustering, and these are standard approaches, cosine similarity. And we can cluster with level 2 labels as ground truth. We didn't actually do this full evaluation, partly because the data is sparse. We cannot really go to the fine grain level. And yeah, so again, we cluster with either symptoms only or herbs and symptoms. Because clustering based on herbs only, it doesn't seem to make sense because symptoms are always. And here's some evaluation results measured by using adjusted random index. And these are different clustering methods. And this is clustering based on symptoms. This is clustering based on symptoms plus herbs. Clearly, the use of herbs helped, and that's not surprising because these labels, these clusters generated by physicians, are partly based on their diagnosis, based on those symptoms. But this last line is an improved version of clustering by using medical dictionary, and shows that it improves the performance slightly here in terms of clustering accuracy. And again, here are some sample clusters and the details are. And here it might be interesting to show that in this kind of medical practice, there are a lot of variations in treatment plans, and that's a reflection of the individualized treatment. So there are patients that are sharing similar symptoms, even if we consider the traditional Chinese medicine symptoms, and they still are treated differently. And this might be because of the history background, their family history, and some other conditions, because they look at a lot of other conditions that are not always well documented here. And this data is actually from the same physician, so this variation is something that's also interesting to look. There are also different symptoms that are treated similarly, and these are some subtle variations that might be interesting, again, for traditional Chinese medicine, or from categorization perspective of patients that can create additional hypothesis space of grouping the patients. So yeah, this work basically is the first study to do subcategorization of the patients. And the main takeaway message in terms of the methodology is that the medical dictionary seems to be helpful in improving clustering and to help us solve the carrier mismatch problem. And we still need to go to the effectiveness. You'll see the effectiveness keyword showing up in all the future work. This is really a major next step, and we're working on that. So the third line is the survival analysis, and this time the main idea we tried is to use a more diverse set of information, external information or knowledge, and bringing together additional knowledge, not just the dictionary, but also molecular network, like protein-protein interaction and other information to help fill in missing values of the medical records. In this case, the medical records are lung cancer patients. And there are also lab test results that are often also available in Western medicine. And so we hope to solve the problems of missing values there. That problem seems more serious than the previous data set we used. So again, this is the problem of variation of vocabulary or the missing data. The typical approach that we have found, at least in the literature, using mean imputation, these didn't really work so well in our case, and we mostly hope to leverage external knowledge to solve this problem. And I should also say, if we don't solve this problem well, what we found is that the standard methods just don't work so well. And that's expected when the data is too sparse, when cannot access the semantic mismatch. I already mentioned this is already existed in some other experiment that we did before. There are variations, questions. How can we get some sense about how well they match if they don't look exactly the same? And then I think people have tried to solve the problem with some approaches by using just more data of similar kind. Using the word-to-vec technique is a word embedding technique where you look at the co-occurrences of words and try to have a low-dimensional space vector representation of words so that the words that are very similar would be close to each other. So our solution here is to use even more external knowledge. And here, for example, molecular interaction knowledge network or known drug targets, all these relevant entities can be brought together along with medical record relations when these symptoms are associated with those drugs. One technical solution here is to actually turn the network data into some form that's easy to use for again, expanding the representation of patient record. Mostly this is to use the co-occurrence information. That's where I have to skip some slides due to the lack of time. But let me actually proceed to that. I think should be better. Yeah. So the idea here is to build a networks like I show here on the left with different types of nodes. Right? And then the goal is to try to learn a vector space representation of each node, and so that we can assess their similarity. So in this case, what we just proceed technically. So the technique used is to kind of score the connection of two nodes based on some vector representation. This is so x sub u is a vector representation of u, x sub v is a vector representation of v, and then this part is the dot product that measures their similarity based on the vector space representation. And these are to add additional inferences of weights on these factors depending on the particular type. And there is some additional adjustment. Basically, this is the hypothesized relation between these two nodes based on the vector space representation. Depending on the actual values, some pairs will be close to each other, some pairs will be not. But then we will then want to maximize the score of pairs that are connected with some paths on our network, and then to penalize or to make scores of nodes that are not connected in this way kind of lower. So the positive samples that we want to kind of fit is the two nodes that are connected by path N, and the negative samples are the two nodes that are not connected by this kind of path. And the path can be customized a little bit based on the types that we want to allow. And then the objective function would be to find these optimal vector representation and weights so that the scores of positive samples are larger than the scores of negative samples. So you'll find that the objective function will consist of these and put together on all nodes on the network, and then we'll adjust to the values of these vectors and weights to make the best fit the network. As a result, we'll get vector representations of these nodes in the vector space. And these can then be used to expand a patient record. We can just multiply the patient record by this vector. Essentially, it causes the expansion of the record. And yeah, so this step was multiply the matrix into patient record matrix. In effect, what would happen is if many values of your patient record are close to some other value or some other entity. According to the vector space representation, you will add that other entity into your representation. So original the value may be 0 in some field, but this analysis shows that a lot of other your existing values actually vote for that value. They are connected, so let's put some non-zero value there. So this provides a way to quantitatively fill in non-zero values, mostly based on the association in this whole network. That's how we can fill in the missing values there. It also causes adjustment of weights of some values, mostly based on this kind of voting strategy. So now, and the data set description. This is a lung cancer data set with 43 patients with certain kind of cancer that I actually don't quite understand. You have 90 patients on another kind, and then 449 unique features. And then there are also some, very importantly, there is availability of survival information, and this is the number of days until death, or in the case there's no death event, the number of days until hospital discharge. And in this network that we used, we have a little bit over 10,000 nodes, mostly are protein nodes, and we have 379,000 edges and 23 edge types. And then we learn these embedding vectors based on that method, and these vectors will be used to modify the patient record representation to improve the similarity. And so, yeah, so I'm going to skip this just to show the results. So the results here are comparing these two groups of patients and look at their survival time. And a main takeaway point is that when we, the right side is a regular baseline clustering method without enrichment by using the information network. The left side is when we do the transformation of patient record representation based on the information network association. And you can see after we have done that, we can see more significant difference between their survival times. And this we're still ongoing. We are still trying to investigate this. But this shows from some perspective that the expansion of patient record is meaningful. It helps capture some true associations. Another case where we also see difference of the p-values that shows that it allows us to group patients more accurately. But again, like I said, this is their ongoing work, and it's just the preliminary results that show the promise of this kind of methodology by integrating medical record data with some additional knowledge. The next step is really to bring this level of analysis to chemical ingredients, so that we can connect this with hopefully genome data if we can acquire them, or other biological databases to more seriously look into the underlying medical knowledge here. Right now, the physicians that collaborate with us are still examining some of the features we nominated for each group. So for these groups, we also use algorithms to nominate what are the separating features, and they're still looking into this. So to summarize, I think I just presented these 3 lines of work of looking at the traditional Chinese medicine record. And one is to do profiling, one is to do subcategorization, and then leverage these categories or groups and try to do survival analysis. And some of the methods that I mentioned hopefully are useful for Western medical records analysis. But also, I think the promise of bringing additional knowledge network together, try to infer patterns, is a direction that's promising in general for data mining, for discovery. Now here we used a very simple method to assess similarity. But I know here you have been working on causal discovery, more carefully assessing the causal relations among those data points. And that kind of analysis definitely is going to be helpful once we can bring together a lot of data, including particularly genomic data. So hopefully when we get to the point when we discover something effective, we can talk again about applying some methods that are developed here to this kind of data. In the future, as you see in this roadmap, we are just here, and even here, the effectiveness is still being investigated. But in the future, of course, we need to go along this direction, and ultimately, hopefully, we can semi-automatically or even automatically discover something like artemisinin to help people discover such knowledge more quickly. And I think immediately the next step that I've been discussing with the collaborators is try to see if we can collect the genomics data, particular related genomics data in the cancer domain, so that we can hopefully connect the two types of data, and a lot of other knowledge pathways to join the analysis. Now, finally, I want to spend a few minutes to talk about the Knowing Center at UIUC that was led by Professor Zhai and Professor ChengXiang. And the main idea there is to build a knowledge engine for genomics. Now, I have to say the knowledge here mostly is based on the existing knowledge, curated knowledge, not discovery, new knowledge. I think the causal discovery might help adding more in that aspect. But basic idea here is you have a cloud-based system for the knowledge network or knowledge base that can help providing knowledge-guided analysis of genomics data. So basically, this is how it works. You open the web interface. I actually was hoping to give a demo, but I did not get the account set up properly. So the user would then log in and to upload a data set in the form of a spreadsheet, Excel data set, your gene profiles, for example, gene expression data. And then you upload it there, and then there are various pipelines you can choose to do analysis. You need to configure the analysis. You might upload additional data as needed, and then you will say, well, I submitted this task, run, and it's going to run, and you don't have to wait there. And once it's done, you will see the results were stored there. You can click on viewing the result, and it will be visualized in some way. So it's like a workbench where you can do your analysis. The main advantage here is the analysis can be done in connection with a very, very large information network that includes some of the network that I just mentioned, but also many more. And the benefit there typically is to, again, help bridge some gaps in your data. Maybe the two genes only show weak similarity here, but then if it's backed up by a lot of neighbors in the network that strongly suggest that they are similar, it helps you strengthen the analysis result. Or if there's an outlier somehow, you might accidentally bring it into your cluster, but this knowledge network might say, well, this one is not really consistent with a lot of other neighbors, so sometimes it can improve the robustness of the analysis. The exact value has, I think, it's still a long way to be demonstrated, but there's a potential for doing that. Right now, we have a system that can be used by biologists to do that. So that's what's included in this network. Well, this is a description of some of the data sets that we're using. And the nodes are genes and properties. The edges are protein-protein interaction, genetic interactions, co-expressions, gene ontology pathway, etc. So, of course, from computer system perspective, you can add additional types. The system can be extended. And again, I have some links you can use to find more information. And so here's what it looks like if you do sample clustering. It's a simple analysis that you can easily do yourself. But then the analysis can be done also by using some information network to increase the robustness. There are some algorithms that you can use. Again, it's an open system to plug in additional algorithms. But here you're seeing that what you're seeing is that there are clusters of genes, and then you can see there these correlations. And in some interfaces, you can move around, you can sort these things, and then you can look at the statistics of each group. like stage 1, stage 2, and even visualize this analysis. So that's one pipeline. Another pipeline is gene prioritization. As here, user uploads a spreadsheet of gene level profiles of a collection of biological samples annotated with a numerical phenotype. So you have the expression and then have the phenotype and this kind of information. And then the pipeline scores each gene by the correlation between its kind of omic value and the phenotype. So it's kind of help you explore a space of genes to see which one seems more interesting. The system doesn't really help you do anything more than that. You're on your own here. But if you have causal analysis and this kind of more detailed hypothesis incorporating the system, I think then the user would be able to then further examine the hypothesis in a more in-depth way. This is another function, and gene set characterization. You have a set of genes, and then we try to kind of use this set of genes as query to find to score other terms like gene ontology terms or pathway, etc. So this just in general, the network would allow you to also use your data as a starting point, as a perspective or view of the database, and then try to explore different types of nodes or using your operators that can compute some output based on this as needed. So biologists can then do this more easily and by taking advantage of the background knowledge. I'm not going to mention all these future, there are some future tasks to be added. I also have done some other projects, but again, I don't think I have time to talk about them. Indeed, I just very briefly mention that we have done work on medical case search. We have explored the clinical nodes to extract the symptom-like terms to help improve predictive modeling of onset of heart diseases, where this unstructured data can help improve the accuracy of prediction. And we've done some work on discovering side effects from online health forums to extract the suspected side effect, and text annotations, annotation of terms on articles and gene function prediction, etc. So I'm going to skip all these, just say thank you, and open for questions, but definitely looking forward to opportunities for collaboration. Yeah. Thanks.
I have a few questions in the next presentation. So my first question is for your probabilistic generating model. So I think the disease and symptoms or even herbs are not independent. So how do you deal with this problem in your model?
Yeah, so here we kind of assume the conditional independence. Given the disease, we assume that the symptoms and the herbs prescribed are independent.
Okay.
That's a way. And in some, so this is actually one problem that I think some previous work did not address. They model the disease together, join the distribution with others, and then the results aren't very good. I think our model seems to give better results in that case. Now, is this coverage? I think it's reasonable to assume that this is the conditional independent, but there may be, right now we have only one disease label there. Certainly, if you go deeper, there should be syndromes. Those are the terms to characterize special, internal or latent symptoms, if you want, and we're not there yet. So a more detailed model might involve those latent variables.
So the second question is, based on my knowledge, so for traditional Chinese medicine, the prescription should be like quantitative, right?
Yes.
So here, the probabilistic model only gives the category of the.
Yeah, that's an excellent question. Yeah, indeed, that's a limitation of this work. We only model the presence or absence of this. Did you prescribe this? But we did not model how much you prescribe, and that information is there. We just did not use it.
Do you think the probabilistic model or such like Bayesian network model has the ability to do that?
Yeah, I think so. We use the multinomial distribution over all these herbs. I'm thinking whether it makes more sense to have multivariate Bernoulli distribution or some other way to model this. But I think it's possible to use additional other distributions to more accurately model this. We just thought that if there's anything interesting, we should be able to see something interesting using this model, and that results seem to confirm that when we talk to the physician. But I think your suggestion is excellent. We should go to the next level. There's some challenge when you make the model more complex, you have more parameters, then it faces a sparseness issue. But we should explore that. Definitely that's meaningful. We did not really explore that. Even with thresholding, I guess some maybe just for normalization. Yeah.
Last question. So you have an embedding model for the similarity. So I was curious how to validate this similarity model.
Yeah, you just ask the same question that our physicians ask us. You show that it seems that after you have done this, it's more significant, but then how confident are we on the results? We are in the process of having them to examine the actual expansions. But in general, how do we validate this kind of approaches, even the knowing engine approach? How do you know you have produced a more robust cluster than I would otherwise produce? That seems a very difficult question. I think we have to engage domain experts to evaluate. I don't know if there's any other way to evaluate. Right now, we're kind of making assumption. If this is indeed better, A should have happened, and we observe that it has happened, so we kind of assume this is true. But now, I don't know how to do that. But one possibility is to have experts to annotate these among these top candidates that you think you can bring to enrich the representation. Let's say if so basically there are missing values here, and you suggest some possible values. We can then ask biologists or medical researchers to look at these candidates, which one do you think is more likely fielding there, and maybe then compare the system's ranking of them with the human generated ranking to have some assessment. Yes?
As you move towards implementing effectiveness in your algorithms, don't you also need to incorporate herb source? I mean, if patients in the U.S. being treated in Maine or Florida with a single drug, they're going to get the same drug. You're in North China versus Southern China, and you've got a TCM doctor, and he's giving you an herb mixture. What's the likelihood that it's from the same source? Meaning, does it have the same effective chemicals?
You mean there are variations of the herb type in different regions?
Sure. I mean,
yeah.
It depends on when you harvest the herb. You harvest it in the spring or the fall.
Right. That's a great point. Actually, that just suggests that it's better to go to the chemical level. And we do have databases of that, but then we need to know the source. And depending on the source,
you could put like
you have more
factor in, so you weight the data a little more strongly if you know the source.
Right. So we might have a source-specific parameter that can be estimated, and then we'll see. It looks like in this region, this group, there's a latent variable that might control some of the variations in the ingredients, and then we might be able to. And that would be also interesting. And that's something we can probably validate if this again.
And I know with TCM, it's not just usually one herb, one symptom.
Yeah.
Right? It's a multivariate thing. So you may have a helper herb, you may have another herb that goes along with this one to reduce side effects. Will your model take into account the presence of these extra herbs?
Not quite yet, and this is also a criticism to the work by our collaborators. And in traditional Chinese medicine, indeed, it's a package.
Yes.
Right now, we have not considered this dependent. Actually, maybe to your question, this is the limitation. We need to model the joint distribution rather than assuming those symptoms are individually independent. And so. Yeah, we also not only making the assumption that the herbs and the symptoms are independent, given the disease, we also made the assumption that all those symptoms are independent, and that's a serious assumption. That doesn't hold in general. And the herb side, it's the same. Definitely, there should be some package and maybe intermediate recipe or something loads that would determine.
And I like the idea of the dose dependence.
Yeah.
Because I think
Yeah,
that's.
that's a great suggestion. We could, I mean, combining your two comments, we could go deeper there just to model the recipes and we'll see if we can recover some of the recipes documented.
If the doctor's giving to you.
There are
Maybe
some,
a special recipe.
yeah, there are some books about these and just so always variations. Yeah.
All right, just for the sake of time, and let's thank you.